Alright, folks, so between the time I did the last video and the time where I just started this video 8 seconds ago, I went and played trivia with the letters, which means it's now late in the evening and I'm sleepy, but I'm going to do my best to make these videos anyway. Hopefully I won't sound too tired for you, and you will still be able to follow my train of thoughts. So first off, you should have made a quick correction on problem 16C. If you have not, then do so now. Please specify 0 less than or equal to t less than infinity. Alrighty, there we go. So let's think about what we're doing here. A, B, and C, three different sets of parametric equations given to us with different t parameter intervals. So we want to graph these functions. We need to indicate the starting point, the direction, and the end point. And then we want to eliminate the parameter for each and compare the rectangular equations. And finally, write a brief statement explaining how each parametric equation differs from the others. So what I'm going to actually do is I'm going to go ahead and do part B first for each equation. So first one here, remember the whole idea of eliminating the parameter is solving for something to then substitute into the other equation. So we want to solve this top equation for t. We could solve y for t as well, but we want to write these equations in terms of y, so let's leave that one by itself. So if I solve this for t, I need to subtract 1 for both sides, so I'll get t equals x minus 1, which I can then take and substitute into this y equals equation 2 times t, where t is the expression x minus 1 plus 5, and we can distribute that 2 to get y equals 2x. 2 times negative 1 gives us our negative 2, plus 5 is giving us a minus 3. So let's think about that equation and then look at this next one. Next equation, notice here we have x equals sine of t, and here we have sine of t. And so we can just directly substitute in x for the sine of t, and we'll see that this equation becomes y equals 2, instead of sine of t, we're going to write x plus 3, which you'll notice is the same equation we got for a, assuming that I knew how to do math and knew that 2 times negative 1 is negative 2, plus a positive 5 is a positive 3. My bad, y'all. So now you should see, hey, yo, look, those are the same equations, although they look different when written in parametric form. They represent the same actual rectangular equation. Well, let's do the same with this last one here. And again, notice 3 to the power of negative t and 3 to the power of negative t there as well, where we can directly substitute x in for that expression to again get y equals 2 times x plus 3. So each of these equations will represent the same rectangular equation, but not necessarily going to have the same domain, since that t value, whatever t value, t range there, t interval is specified, it's going to dictate where we're actually looking at this graph. So what I'm going to do is I'm going to create a quick data table to determine what these points are. So let's think about this first one. What I'm going to do is a t column, an x column, and a y column. And I'm going to start with my lowest t value of 0, and then I'm going to go by integers up to 6. And you should see some pretty distinct patterns forming that will allow you to jump to some conclusions. So first off, when t equals 0, what is our first x value? Well, we have our x equation right here. Let's do all our x's and then all our y's. So if x is 0, then if t is 0, then x equals t plus 1 gives us 0 plus 1 is 1. If t is 1, we get 1 plus 1 is 2. If t is 2, we get 2 plus 1 is 3, etc., 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 increasing by 1 each time, because for each t value, we know that x is 1 greater. That's what x equals t plus 1 means. So now let's look at our y equals. And here we have 2t plus 5. So if t is 0, then 2t is 0, so we get plus 5 for our first y value. If t is 1, we get 2 times 1 is 2, plus 5 is 7. And again, you should recognize that this is a linear function with a slope of 2, so each of these points is going to increase by 2. So 5, 7, 9, 7 if you can't do math, 11 if you can, 13, 15, 17, like that. So I know my starting point is going to be 1, comma, 5, that first pair when t is 0, and my ending point is going to be the point 7, comma, 17. So I can sketch a quick graph here. And so let's go ahead and graph this equation real quick. So starting point is 1, comma, 5, so x value 1, y value of 5, right there. Let's plot that. And then our ending point, notice it's going up in a linear fashion. X is increasing by 1 each time, y is increasing by 2. So we're going to go up to the x value of 7, and we're going to go up to the y value of 17. And so I'm not feeling like drawing in all those little tick marks, so I'm kind of going to label the important pieces and draw a line between them, because it's linear, so I can absolutely do that. Orientation, let's indicate the orientation by putting an arrow in the direction of this function. It's going to start right there at 1, comma 5, and it's going to end over here at 7, comma 13. So there we have it, our start point, our end point. It's just following that linear line from left to right, up that graph. Okay, well, let's do the same thing for B now. So let's go with a T column, an X column, and a Y column. So where should we start? Well, we're dealing with a sine function, so let's go back to our friend, the unit circle, and let's think about what sine values will be easy for us to calculate. Well, sine of 0, we know sine of 0 is just 0, because remember, sine is your y values. Sine of 30 degrees, or pi over 6, is another easy one. That's 1/2. The next two sine values that we know are root 2 over 2 and root 3 over 2, which don't help us. But then we can go straight up when sine is 1, and then we can go to the reference angle of 30, so 150 degrees. And we can go back to 0 right there, and then again it's going to run through those values this way as well. So kind of some key points on there, easy sine values that we know. Those are the ones we want to look at. So let's start listing some out. First t value I'm going to do is 0. Next t value I'm going to do is pi over 6, which is the same as 30 degrees. Next t value I'm going to do is pi over 2, straight up 90 degrees. And then I want you to recognize something. I want you to recognize the pattern in the psi values. Think about what we have. This sine value is 0. This sine value is 1/2. This sine value is 1. This one is again 1/2. And this one is again 0. So once I get up to pi over 2, then the next two just repeat. And so the next distinct value is going to happen here at 7 pi over 6. And then the next one at, what is that, 3 pi over 2. And then again we're repeating. So let's go ahead and look at these values. So when t is 0, we just have sine of 0, which is 0. When t is pi over 6, we have the sine of pi over 6, which is 1/2. When t is pi over 2, we get a sine value where your graph is straight up, which is giving us our maximum value of 1. And then what happens after that? Well, then it repeats that value and that value. So we secretly have another 1/2 and then a 0 in there. And then we hit that value right there at 7 pi over 6, where the sine is negative 1/2. and then we hit this value right here where the sign is -1, and then again we repeat that -1/2. We repeat that 0 as well. Maybe I should just make that clear. Alright, so I've gone through and I've labeled all those pieces now. 0, pi over 6, pi over 2, 5 pi over 6, pi, yada 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 yada. So we get a distinct pattern here. 0, 1/2, 1, 1/2, 0, -1/2, -1, -1/2, 0. So notice that we are kind of bouncing between positive and -1, starting at 0 in increments of 1/2, which is interesting, but again should make sense because x is just our sine function. So think about the graph of sine. It oscillates between -1 and 1. Okay, well now let's look at our corresponding y values. Well, I'm going to use the fact that y, when you eliminate the parameter, is 2x plus 3, and I'm just going to use those x values rather than repeating the process of evaluating the sine of t and then multiplying by 2 and then adding 3. So 2 times 0 is 0, plus 3 is 3. When the time is pi over 6, the x value is 1/2, which means I have 2 times 1/2 is 1, plus 3 is 4. And then I have pi over 2, which gives me an x value of 1, which gives me 2 times 1 is 2, plus 3 is 5. And notice what's happening for y. Y is going up by 1 each time. But then my next x value goes back down to 1/2, so I need to go back down to 4. And then my next x value goes back down to 0, so I need to go back down to 3. And then I hit -1/2, and you could probably follow the pattern, but if you can't, we have 2 times -1/2 is -1, plus 3 is +2. Look, 5, 4, 3, 2. And then I go another -1/2 to the left, so I need to go another 1 down. But again, 2 times -1 is -2, plus 3 is +1. And then I'm back at -1/2, so I go back to 2, then I'm back at 0, so I go back at 3. So here again I have my starting point, and here I have my ending point. So now I'm starting and I'm ending at the same exact spot. So let's think about what this graph looks like in comparison. We know that it's technically along this same line, but it's happening in a different area. Here it's happening when x is between 1 and -1. So when I plot this, well, let's go a -1 and a +1. And notice the y values go from 1 up to 5. So 1, 2, 3, 4, 5. So where do I start? Well, my first point is at 0, 3. Notice that is the y-intercept of 2x plus 3, so that makes sense that it is there. And then what happens from there? When x is 1/2, we go up to 4. So halfway in between there, we're at 4. Then when x is 1, we're up at 5. And then we go back to 4. And then we go back to 3. And then we go, when we're halfway in there, we go down to 2. And then we go down to 1, and then we go back up to 2, and then we go back up to 3, start where we finish. So that is our line. It's going to look like that. It's linear, we knew that. But let's think about how we can indicate the direction of this curve. What I'm going to do is I'm going to show that it started here, and it went whoop up, and then it went back down, and then it went right back up to where it started. That's kind of how I indicate that. That is by no means an official way to do that. That's just how I do it, which I think makes sense. A little start here, go backwards, and end where I started, where it's symmetric like that. Okay, let's do this next one here. Again, I'm going to make a table. I'm going to have t, I'm going to have x, and I'm going to have y. And actually, I'm not going to make a table for this because I don't want to. I'm going to analyze the function and use what I know about these functions. So, first off, notice we're going from t equals 0 up to infinity. And think about this graph. X equals 3 to the -2. I'm sorry, 3 to the -t. And now, what I'm going to do is I'm going to ask you to do something weird here and think of the graph y equals 3 to the negative x. What does that look like? Well, 3 to the negative x is really saying, think about what that negative on your x term does. It flips it. Think about what 3 to the x looks like. It's just an exponential curve like that. 3 to the negative x is just an exponential curve like that right there. And so, where is our starting value? So notice what I've done now. I've taken that graph, y equals 3 to the negative x, the function that I am familiar with from earlier in the year, an exponential graph that has been flipped horizontally. I know that that point right there is happening at 0, comma 1, because 3 to the 0 is 1. And notice how I've labeled my axes. I've taken that general shape of y equals 3 to the negative x and compared it to what I actually have, x equals 3 to the negative t. So you need to think of that vertical axis as x, the dependent axis, and the independent axis is that time t. And so I have that function there, and I'm looking from t equals 0 up to infinity, which means I'm looking this direction. So I know that is my starting point, 0, comma 1, which is telling me that when the time is 0, the x value is 1. So I'm going to start at, what did I just say? When the time is 0, the x value is 1, which means the x coordinate is 1. What's the y coordinate? We'll plug it into our equation. 2 times 1 is 2, plus 3 is 5. That should mesh up with this point right there. And do we have it over here? Yep, we have it right there as well. 1 comma 5 happens to be our starting point now. And think about what's our ending point. Well, what's the limit as 2 times 3 to the negative t plus 3 goes to infinity? I didn't write that in proper notation. But let's maybe do that. Think of this as the limit as t goes to infinity. That's how I should write that. What is the limit as t goes to infinity of the y value here? And similarly, what's the limit as t goes to infinity of our x value, which is just 3 to the negative t? Well, think about what's happening. That exponent is getting very, 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 very big. But think about what happens when you're dealing with a negative exponent. Well, that's the same as rewriting this as the limit as t goes to infinity of 1 over 3 to the t, which should allow you to see that the limit for this is going to be 0, which means my x value is going to 0, and my y value is then going to go to 3. So you can think of our, quote, end point as the point 0, comma 3. Will we ever get there? Technically no, because it's going on forever, but we do know that is where it's going. And if it had to end, that is where it would end. So we can graph this in a similar manner. We are starting at the x value 1, comma 5, and we are ending at the x value of 0, 0, comma 3. So we're starting here, and we're ending there at the y-intercept. So there's our start, and there's our end. So what's the connection between all of these functions? We'll look at their form. The y is always in the form of 2 times some crap plus 3, and the x is always in the form of that some crap. Not quite as easy to see it in the case of a, but when we solve the parameter and simplify it all out, we get the same thing.